right. We are in week 6, May 9th. I am doing what will probably be the shortest lecture of kinematics today on assignment number 7 to get you started on that. And you have this week to work on that, and it will probably go into next week. Looking ahead, next week I am seriously considering, and I hope you're not too disappointed, of not doing this assignment number 8.
What?
And giving those of you that are up to date a little bit of time to work on something else. Those of you that are not up to date, time to catch up without doing any more lecturing next week and having some open lab times available. Seriously considering that. And the other class is sort of in agreement as well. I didn't tell them those words exactly, but I probably will. So I hope you're not too terribly disappointed in doing less work. Okay, consensus is. And then we'll start working towards finishing up and getting everything in, because June 6th is an open lab to try to get things in, to try to get you finished off and completed, actually before finals week, and finished up. All right, that's the plan, and I may even stick to it.
Yes.
All right, come on, let's go. All right, I've been working my way through your working drawings of gear number 1 and looking at those. So assignment number 7 begins with instructions. Again, you can use your program of choice, and I included AutoCAD 3D solid modeling in there. I think it's a little more cumbersome to actually end up with a 3D solid model out of it in an STL file. I think you'd have to create it and import it into Inventor and do a workaround that way. So you might just kind of consider SolidWorks or Inventor to create a 3D solid model of a spur gear. When your 3D solid model is complete, you will then save it as an STL file, a slice file, to be able to create a 3D solid model out of it. Have all of you in here done either CAD 199D or are doing CAD 105 right now? Anybody not have that class yet? Okay. You would be able to create your own 3D printed model. So I'm counting on that taking place. Anybody that hasn't done that particular class yet, we'll work out the details of that. All right, so you need the STL file to make your 3D printed, then it has to go through the MakerBot software to convert it into a file that the MakerBot can create. And we have numerous machines in here. Since it's Tuesday, Thursday, when you are creating your slice, your MakerBot file, you have to preview it and make sure that the time element is such that you're not going into my class on Tuesday evening and having the printers going, or Thursday evening going into the SolidWorks class that takes place in this classroom as well. In other words, if your file's going to take 3 hours and it's 4 o'clock in the afternoon, don't start it. It'll get paused or canceled or something, depending on my mood at that particular time, if it's Tuesday. Eric.
What time is that Thursday night class?
Starts at 6 o'clock. So it has to be all completed by 6 o'clock. You can sit there, that's fine, but we don't want the machines running, interrupting a lecture portion. All right, you've got some information, some design information in the project. The diametral pitch, DP is 8, pitch diameter, PD is 3, number of teeth, N is 24, outside diameter, OD is 3 1/4, face width, which is what the thickness of the gear is actually going to end up being, is 3/16 of an inch, A, so that it doesn't take up an extraordinary amount of material, and B, it doesn't take hours and hours to run. And yet it still gives you a good idea what it looks like. There is a bore diameter that goes into the gear in the middle, 7/8 inch diameter. There is also a mechanical connection. Keyway size is 3/16 of an inch by 3/16 of an inch. That means that the width of the keyway that you are creating in your model is 3/16 inch wide. And how deep is it going to be?
3/16. Half of 3/16.
It's not going to be 3/16.
No, 'cause the
Half
other
of it goes in the keyway and half of it goes in the shaft for the key seat. That is an error that a few people have made over the years. They go, oh, 3/16 by 3/16, and the keyway ends up being twice as big as what it's supposed to be. And I'm being really generous in giving you that information ahead of time. Yes. So it's 3/32 height by 3/16 in the keyway. The pressure angle is 20 degrees. We're using a drafting technique called the involute curve. So it's a pretty close approximation of what the gear is going to look like. With the working drawing that you did previously last week, the cutting data that you calculated out and verified the numbers that were there, that's the information that the machinist would take, and basically it's enough information that they would get their cutters out, take a blank, and mill out the teeth for the gear. So we're doing something that's fairly close. Every gear's diametral pitch needs to match for the teeth to mesh. I've got to try to do a little adjusting on my checking fixtures because the precision and tolerancing on these machines don't match the $40,000 machine that I made my checking fixtures from several years ago over at Sylvania with the machine tech program that was there. They had this really super duper printer that was pretty accurate. So I'm trying to adjust it. I tried last year and never quite got to it. What thing that I would do is I would take a shaft that I 3D printed, make sure that it fit, your gear fit on the shaft, the diameters matched up, and then used a key piece to make sure that the keyway was correct. Then I had another fixture that had the center to center distance and put one that was turned in with one that was already made, and they were to mesh. And that was the problem I'm having, is the diameter of those, they're kind of all over the board with 4 different machines, and it's kind of hard to speculate because I can't make it too big and I can't make it too small. So that's my problem. I'm working on that. So the idea was that if the shaft went in and the key went in and it meshed with another gear, you passed. If it didn't, you failed. Basically, go, no go kind of a situation. No redos. So I'll work that out. Okay, questions on that so far? All right. Yes.
I got one. You said we could use SolidWorks or Inventor. Can we use Fusion for designing the gear?
Oh.
Because Fusion's just the one-stop place where you can go straight from Fusion to the.
To make your bot, it's super easy.
If you want to use Fusion and you get what I'm asking for, I don't have a problem. That's the first time anybody's asked about that. Sure.
I think that's what most of us use in Justin's 105 class.
Okay.
Yeah.
If you can create, the shape of the gears and all that kind of stuff, that's fine with me. Cool. Yeah. Eric?
Yeah, I don't get how you got that 3/32 for the keyway.
I can explain it to you. Okay.
Thanks.
All right. The 3/32 just came from an arbitrary size, basically.
Oh.
Is kind of how I did it. All right. And let's go back. And I I hope your brains are all nice and able to absorb things this afternoon. This is a step-by-step written instruction sheet. It will probably make not much sense, but I'm going to go through it anyway, because I made the other class endure it as well. First step is to construct an arc or a circle representing the base circle. That means you have to go back to the textbook and look up the formulas. The base circle doesn't really have much to do with the drawing, the gear itself, but I want you to do the calculation, so don't let that throw you too much. Then an arc or a circle representing the pitch diameter, constructing center lines, intersection of this vertical center line and the pitch diameter, draw a horizontal line, construct a 20-degree line from the intersection of the vertical center line and the pitch diameter, construct a line from the center of the circle perpendicular to the 20-degree line. Using endpoint of the line that was just constructed as the center of a circle, draw a circle whose radius is pitch diameter divided by 8, which equals 0.375. I'm even doing some of the calculations for you, some of them. And then trimming the circle to an arc. At that point, step 9 and 10 and 11 are calculations that I have done for you. A lot of it's based off of the formulas of how to determine gears in the textbook. There's a circumference of the pitch diameter. That's the distance all the way around. And to figure out how much distance along that circumference, in inches it is, you're using this. You're taking the circumference of the pitch diameter by 360. This will give you the distance each degree is along the circumference. That figure should end up being, if you actually calculated it, but I'm giving it to you, is 0.026. So every degree along the circumference is 0.026 inches as we traveled around the circumference. The width of the tooth is the circular pitch, CP, divided by 2. The circular pitch is equal to 3.1416 divided by 8, which is the diametral pitch. That gives you 0.3927, which is then divided by 2, which is equal to 0.196. So you got a tooth width, and that gets divided in half. These are just calculations to give you the process of determining some angles as you develop your tooth in a drafting mode. Dividing the tooth width by 0.026, 0.196 divided by 0.026 equals 7.54. This is the degrees on the circumference between point T and point S that is on the handout, which I will get to. So, you know, it's about at an understanding level here. I can see your eyes. They're glazing over already. Like, what are you talking about, Truman? But it will be crystal clear as mud pretty soon. All right, now you get back to doing the actual construction stuff. Constructing a line from the center of the circle to the intersection of the arc and the pitch diameter. Rotating that line 7.54 degrees or creating another line at an angle of 7.54 degrees between the lines. Constructing a line between the endpoint of the rotated line and the intersection of the arc and the pitch diameter. Constructing a line perpendicular to the line just constructed and the line's midpoint, which gives you an axis line around which you can mirror the first arc that was created way up in here, 6, 7, and 8 steps, and then have the other side of the tooth form. Constructing an arc or a circle that is offset the addendum from the pitch diameter, so you have to calculate that. That's going to be above the pitch diameter. Constructing an arc or a circle that is offset the dedendum from the pitch diameter, that's below the pitch diameter. Constructing an arc or a circle that is offset the clearance from the dedendum, which happens to be 0.02. Extending the arcs to the dedendum. And then filleting the arc and the clearance with a radius of 0.035. Trimming the upper part of the tooth profile, and then you should be able to array that tooth construction around the center point and get 24 teeth. That's the idea. Alright, that's the written instructions. And fortunately for this class, the confusing handout that I made yesterday and put up didn't have all three of the circles in there, and it was confusing, and I had to redo that. Now here's the visualization of those steps. So going along with step by step, so step one was talking about creating the circle, which is the base circle. Step two was creating a pitch diameter circle with a diameter 3. This is the OD, 3.25, sorry. Step 3 is center lines, horizontal and vertical. Then it talked about creating a horizontal line from the pitch diameter and the intersection of the vertical line. Creating a 20-degree line off of that. Taking the line from the center perpendicular to this 20-degree line. Using this as a center point for a circle that has a 0.375 radius, which creates that. Drawing a line from here to the intersection of the arc and the pitch diameter, that's step 12. Then making another line or creating, rotating this around to get another line that goes to this intersection point here. Then that creates a line between those 2 points, T and S. You do a vertical line that's basically bisecting that line in 2 equal parts, perpendicular at this midpoint, and then using that to mirror this arc around here. And yes, that's a little hard to see, so I replicated it up here. So you've got a line that comes to here. That's this line. This is now 7.54 degrees to give you the tooth form width that was calculated off of taking the circumference, dividing it by 360 degrees, and all that. This is the line from S, T to S, right here. There's your perpendicular, bisecting, here's the arc, and it gets mirrored over here. Easy enough. Then the outside diameter, then there's another page that goes on from there. That's another PDF. It goes into step 17, 18, and 19. It talked about adding the addendum from the pitch diameter. That gets you here. What you would find out is that the OD, the 3.25, and the addendum are within thousandths of an inch of each other. So you could probably get by with the OD, but the addendum, the height of that tooth is much more accurate, because when you get 2 gears that mesh together, you don't want them to bottom out. That's part of the dedendum and the clearance measurements that are going on in the calculations that are done. Then it talked, step 18 was the dedendum from the pitch diameter. That's this line right here. Then there's a clearance that comes in, and then extending these arcs down to the dedendum to get that part of it. And then there should be one more illustration that talks about the clearance and then filleting the arc and the clearance line in here, and that then also gives you a clearance so that the teeth don't bottom out. There's supposed to be a clearance between how they mesh. You get that all done, you should be able to array it and get your 24 teeth in there. Most everybody has been able to follow along. I did get some questions yesterday. I think I have been able to clear that up with the drawing itself, because it was a little confusing with only 2 circles in there, and everybody's kind of like. And the other problem was I had the horizontal line going off of the wrong circle. Other than that, it was pretty clear. So I fixed it up, and you should be able to create your profile and then extrude it to 3/16 of an inch. I know, there's probably not questions right now, but there will probably be questions later. So, let me just leave the tape running for a second. I'm gonna go back and grab an example of what these things kind of end up looking like. So, that you can kind of see what we're after. All right, this is one that was done several years ago, and it ended up being way too thick. The other machine was able to run them a little faster. So you've got your 24 teeth here, the approximate shape of them. There's the bore, and there's the keyway in here. So I just kept that as an example.
Are we gonna pass these around?
I can pass them around, yes. So when I was checking these originally, and this is one I'll probably have to modify just a little bit. I had this shaft that I 3D printed, and I had a 3/16 by 3/16 key. So I just stuck the two of them together. And here's one that was done last year. Oh, the other thing, sorry, the other class. I let people do whatever they want to design-wise inside. Because it doesn't have to be all that structurally sound. You know, the more you take out, the less durability you have. So I've been getting interesting designs over the years. I probably should send an email to the other class saying, well, you know, if you wanted to kind of fancy it up a little bit.
Wouldn't take as long to print either.
It wouldn't take as long to print, that's true. So the idea was that the shaft would go in and basically slide in here a little bit. So some of them ended up working out pretty good, and others just the tolerancing of the print. So that would be a passing grade on that. And then I would take it over and place it on my little fixture that had this correct center line, and basically it was supposed to do this. That's the other half of the passing grade. If all those things fell into place, voila, we had a winning thing. Now this little one right here, I'm not sure if you can see it really well, but that's a 3/16 by 3/16 key. And that's too big. Half of it goes into the keyway and half of it goes into the shaft. And if I actually put this in, it's probably a little, actually that one ends up being okay. Must have been one other one that I had somewhere.
Just slid all the way through.
Yeah, that still looks too big. So that's kind of the idea. And then you get to take your gear home. Put a magnet on it, attach it to the refrigerator, and say, see what I did. And you can too if you take the Cadd certificate program or something like that. All right, so any questions? So there is supposed to be a space down here. I've had a few that bottomed out over the years. And, so that's the idea. And then, so that's one. Let's see, maybe this was one that didn't quite work. Nope, that one was working too. So maybe we fixed it. So that's kind of the idea. So this is another shape that somebody did. I've had snowflakes in here. I've had interesting little designs. But yeah, it wouldn't take nearly as long to print either. This would probably not be a great gear because there's not a lot of material here and it would probably fail. Unless there wasn't too many forces involved with it. So that's the assignment. That's where we're going with this thing. All right.